I just realized I was doing the presentation. I got 3 minutes in, I wasn't recording. Anyway, hello, I'm Tyler Trott, and I'm presenting again my final project for CSC 466. I found myself frustrated, not only because I forgot to hit record, but with the inefficiencies of traffic systems, especially in cities like Victoria. These inefficiencies got me thinking about how we can use technology to improve traffic flow management, especially in a networking type of way. While downtown Victoria may not have the same extreme congestion as cities like Vancouver, LA, maybe New York, I believe it serves as an ideal test bed for optimizing traffic flow. Congestion is a major urban problem. It's not just annoying, it wastes time, it increases fuel consumption, and of course, contributes to pollution. In downtown Victoria, traffic flow could be significantly improved with better coordination between traffic signals and maybe coordination between construction, but I cannot help with that, unfortunately. However, managing traffic across multiple intersections requires real-time data and complex computations to adjust the signals dynamically. There's also another catch on top of this. The networks of sensors typically used in these systems have very, very limited storage and computational capabilities. This problem lies in the architecture of the networks, or more commonly referred to as wireless sensor networks, or WSNs for short. WSNs are designed to gather small bits of data, maybe like environmental, like temperature, maybe number of cars in our context. And it uses very small, low power sensors that send this data wirelessly. However, these sensors have limitations when it comes to storage and computing power. So, how do we collect and process vast amounts of data without actually overloading these poor little sensors or the network itself? This was a critical challenge to overcome, especially when we want to apply something like machine learning to improve traffic predictions. This was quite the undertaking of a project, and I am tired. Anyway, what the solution I've come up with is based around federated learning, which I believe is a good potential solution to this issue. By keeping data processing local to each sensor and only sharing model updates rather than raw data, we avoid potentially overwhelming the network with unnecessary traffic. But even with this approach, we still need to optimize for efficiency. To do this, we combine our FL network with gossip protocols. If you've seen my reading summary 4 video, first of all, thank you. You will know about FL and gossip protocols. If not, here's a clip from that video for you. Federated learning is proposed as a decentralized mechanism using the on-device processing capabilities and the collected data to train the model in a distributed manner. What this means is that each member of a federation, a node in the network, of the distributed learners trains its models locally using only the data it possesses, and then sends it to another node that is in charge of transmitting it to an aggregation point or elsewhere. This is then sent back to the original sendee for further training and use locally. More on this later. A fun example of FL that everyone knows of is the Hey Siri vocal classifier feature with Apple machines. Each phone exists as its own node and updates its model around its owner's voice and speech patterns, sends this information to Apple. Apple updates the global model and sends the updated model back to the phone. Gossiping is a mechanism that allows for a set of nodes to exchange local information such as measurements and or model parameters to reach some global or partitioned consensus regarding such information. The paper proposes an idea of integrating this mechanism into a federated learning network to potentially reduce the number of transmissions needed to be sent in total. This would lead to system performance concerning energy consumption, network lifetime, and network overhead, as gossiping was initially conceived to solve the consensus problem by exploiting resources at each node to decrease the amount of data that needs to be transmitted. The objective of gossiping in a WSN is to allow all nodes to share some estimation of the average of models that exist in that network. Now that we understand FL and gossip, I hope I can present the actual solution that I've spent the last few months working on. FLARE, which stands for Federated Learning for Adaptive Road Efficiency. A quick breakdown of FLARE. The idea, which I've notioned a little bit earlier, is that each node in the system represents a traffic light. Each traffic light, or node, or sensor for the traffic light, will perform local training using traffic data collected for that intersection and share the results with its neighbors. This could be literally a neighboring intersection or light. The gossip protocol helps to propagate these updates across the network, allowing all nodes to collaboratively improve their models. This decentralized approach makes the system more resilient, efficient, and adaptive to changing traffic conditions. Because, you have things like weekends or maybe events or everyone's off at work or dropping off children to school, etc. But before we jump into the simulation, here's a simplified diagram showing how the network is actually structured, or how I would want it to be structured in a partitioned way. The system is built around a mesh network with four clusters, A, B, C, and D. Each cluster represents a group of local intersections, and within each cluster, all nodes are fully connected. Nodes within each cluster can communicate with one another to update their models, but they can also communicate across clusters, forming a global network for knowledge exchange. So, if an intersection needs to know what another intersection from a different node is doing, they can grab that information. The gossip protocol works by having nodes A, perform local training on traffic data, B, send model updates to neighboring nodes, and C, receive updates from neighbors and adjust their models accordingly. This setup ensures that the traffic management system evolves collaboratively, with each intersection improving its traffic predictions over time, all while maintaining decentralization. On top of this, we're minimizing the need for centralized computation, which would suck in this scenario when you're considering scalability. What's happening behind the scenes in terms of the system's architecture before we dive into the core simulation. So, the most important part right now, or for me, is the makefile. The makefile is responsible for orchestrating the entire process. It first runs a Python script that parses the spreadsheets graciously provided by the city of Victoria. Thank you so much for that. That was awesome. And extracting key traffic data such as volumes and classifications for different directions. This data is then cleaned and saved as CSV files. The locations are standardized for consistency because it was a very painful process to go through. For example, any spaces or special characters like ampersands, I just remove them, and everything is converted to lowercase to ensure matching across files because Python is so difficult to work with. Like, why? Why is it so hard? Once the data is processed, it's used in the core simulation. Um, for the ML model, I used a linear regression model that I applied to predict traffic behavior based on that data. This model is trained on multiple data sets provided by the City of Victoria, and its performance is evaluated using metrics like R squared. The model's weights are adjusted to improve predictions, allowing for a more accurate representation of real-world traffic patterns. Uh, with the spreadsheets and data that the City of Victoria have sent me, we have times like rush hour, AM, PM, midday differences, etc. Finally, this data feeds into the C++ simulation code where traffic predictions influence how vehicles behave under various network protocols, such as federated learning. Now, let's dive into the simulation itself. I used OmNet++ to build this federated learning network, and it had its times. Here's how it works in practice. So first, we have nodes representing traffic lights, of course, maintain a local model, which consists of a set of weights. These weights are adjusted during local training using traffic data from the intersection itself. Once a model has been tweaked locally or updated, the node sends its updated weights to neighboring nodes. The node also receives model updates from its neighbors and uses these updates to adjust its own model. The forward model update function ensures that gossip messages are properly exchanged between nodes. Each node evaluates how well its model is performing. I implemented this by just having a simple evaluation function. I mean, it doesn't really do much. It just checks the accuracy of its model's predictions. That is to be discussed later, though. This approach ensures that even without a centralized system, all traffic lights collaboratively refine their models, which again improve traffic predictions across the network, which is what we want. This in turn allows the system to better control traffic flow in real time. As a side note, if you've been keeping up with my project updates, again, thank you, very committed fan. You're probably wondering where my OSM files are, the actual vehicle simulations of downtown Victoria. These seemingly disappeared from my project updates. This project was a lot more gruesome and time-consuming than I was hoping it would be. I also have other classes and a job, um, along with a personal life. So, anyway, looking ahead, here's what's next for the project if I ever desire to work on this again. This was a lot of fun, and I do kind of want to. Python script optimization and data flow. Right now, the primary focus is on getting the Python scripts to read and process the CSV files correctly because, oh my God, that was so painful. Ensuring that the pre-processing is seamless, I think will make the integration of the traffic models smoother and allow for more actual effective use of the data in the simulation to train the models to begin with. That would be very helpful. Federated averaging or Fed average. The next step, I would say, is to actually implement federated averaging. This will allow each node to average the model updates it receives from its neighbors and adjust its own model based on this averaged value rather than, completely switching out what model it has right now or at that moment. This technique is known to improve the convergence of federated learning systems, and it will, I think, enhance the model's robustness like tenfold. I think I would also want to have maybe an improved model evaluation and optimization. I would want to implement more detailed evaluation metrics such as accuracy, precision, recall, and maybe like an F1 score to better assess the performance of the model and make more informed adjustments rather than just kind of letting things happen and then switching the bad values. Um, Optimizing traffic control logic. The ultimate goal of the project is to optimize the traffic control logic for intersections. Once the model can actually predict traffic flow with higher accuracy, it will be integrated into real-time control systems to dynamically adjust signals, hopefully improving traffic flow and reducing congestion. But I mean, that's way down the line. But that is the dream. I think, of course, you want to worry about scalability and real-world traffic data. I envision scaling up the system to simulate larger networks and integrating real traffic data from Sumo to see how the model performs in more complex environments. Let's say, like in Las Vegas on the Strip compared to maybe streets that are alongside it. I just think it would help test its real world applicability and scalability. Some final notes. Um, Please do not try to run Python in C++ in Omnet. It is just unbelievably painful. Like, it's just, I mean, once you get it working, it's pretty good, but like, why? What is happening? Um, but yeah, if you have any questions, um, I want to have my performance analytics up, but again, Python is just so painful. I will try and get the logs and everything as soon as possible whenever Python decides to be kind to me. This is a really fun learning experience, though. I've never built anything in Omnet before, so learning how to actually build networks in NED files and just doing C++ plus plus again. I haven't programmed C++ plus plus in years, so that was a lot of fun. Yeah, so thank you again to the city of Victoria for doing surveys in the first place. This data set was from this year. And they gave me data sets for the last 5 years. So honestly, to train a model, like I'm not even worried that the model would be able to find maybe anything to work with. It's definitely a doable process. Proof of concept now exists once Python becomes my friend. But yeah, if you have any questions, please let me know. I have a project log that I was providing updates for during any session I was working on this project with. Um, so if you have any questions, you can also refer to that if I am not free. Um, Thanks for watching.